All right. Hello. All right. So yeah, as I mentioned before, you can scan the QR code in the bottom right, and that will get you a copy of my slides, which is what you guys will see today. Thank you all for coming out on a Tuesday, probably when you don't have class or you've only got lectures and stuff like that. I've told a few of you about the seating arrangement. So I guess I was saying like the first and second year teams kind of towards the front, second and third year teams in the middle, and then whatever. But it doesn't really matter. You can stay where you're seated if you're out of place or whatever. But what this tells me is that third to fifth year students have learned that you don't need to go to lectures. You can watch the recording. No, I'm kidding. But I'm here to help you out. The reason I've kind of gotten you guys to sit in this particular way is just so that later during like the workshop-y kind of portion of today, I can come around and I kind of got an idea of how much you already know, so I can give you more or less detail based on what you've already done. But yeah, thank you all for signing up to the CEVSOC student project. As you probably saw in week 6, the opening night, there's heaps of people signed up for this. I think there's about 150 students signed up for this, and that's 32 teams. So it's a lot. For reference, I was like a demonstrator for DESN 1000 last term, and for the balsa wood tower that they had to build, there was 26 teams. So we're about like in the ballpark of 20% larger of a course, quote unquote, than DESN was, at least for that project. But there's a lot of people. They're probably not all here today. That's probably because I'll watch the recording later. But anyway, I normally say stuff like thank you to the organizers at the end, but because people will probably come and go throughout today, I'll just say it now. Really like to show my appreciation for Jack and Liam, who are at the back. They're the organizers from CEVSOC. They're the development team. So sorry guys, if you could just give them a round of applause for me, that would be really nice. They've put in a ton of work for you guys to set up this project, the timeline and everything. And also, this is the first time that this kind of thing has happened before. We've never run a quote-unquote course or like a little student project, and hopefully you get a lot out of this, a lot of like practical kind of design skills that you wouldn't normally see so much throughout your normal degree. So it's really cool, and I hope they keep doing this sort of stuff. Okay, so about me, right? And I basically, okay, well, I'll explain what this slide means, right? On the left, this is kind of my credentials. A lot of you guys probably like first years or second years who sat towards the front, and you might not know who I am. I'm kind of a demonstrator for a lot of structural engineering courses, and my experience is that I'm in my first year of doing my PhD. I've got 1 year of graduate design experience, so I was a structural engineer graduate last year. I've got 1 year of site engineering experience through my internship, and yeah, I've been a tutor for these kind of courses. So it's Eng 1300, solid mechanics, concrete, DESN 1000. For seismic design, you don't encounter this unless you decide to do structural dynamics, which is like a 4th year elective. So a lot of these concepts are actually going to be quite complicated, but I'm going to try my best today to break it down for you. I've dealt with it a little bit during work, like seismic design, but because I wasn't like, I'm not an absolute expert on this topic, I decided to consult my friend, a fellow PhD student who's got more experience than me. He was a designer for several years, and he's done a lot in terms of earthquake and timber design. It's kind of perfectly suited for this project. But yeah, so hopefully this gives you guys a bit of confidence in what I'm saying in terms of I've tried to like, I guess, upskill myself so that I can do a better job teaching you guys. So yeah, I consulted my friend basically is what I'm trying to say. Okay, so here's going to be the contents that we're going to run through today. So there'll kind of be 2 halves. So first I'm going to tell you I'm going to reiterate the project timeline. I think you guys have seen this before, but we'll just show it again. But now we'll kind of give you a detailed project brief on what the parameters are that you're designing around and essentially what you have to do. And then I'll give you guys some time to discuss as a team. like any initial ideas that you might have, and then after like this little discussion where I'll come around and chat to you guys, I'll do a bit more theory stuff. So it'll be on the idea of cyclic loading, energy dissipation, lateral stability. I'll touch on these last few topics a bit briefly because essentially the lecture that's going to be run by an actual lecturer tomorrow, Daniel Ashea, will be on these kind of topics. So lateral stability systems, materials and considerations, and connection detailing. And then finally we'll do another group discussion at the end. So the idea is that after we've kind of covered theory, hopefully it'll spark some ideas in your head and for your group, and you guys can kind of share and toss up some ideas on where you want to go. And I'll come around again at the end and we can workshop those ideas together. All right, do you guys have any questions off the bat? Feel free to ask questions at any point throughout today's talk. The whole point is we'll do it together and we'll hopefully get something out of it, knowledge-wise. Okay, so project timeline. Yeah, so last week was week 6, and that's when you had the little opening night where they briefed you guys on the projects. Hopefully, if you were able to make it to that, you saw there were so many bloody people doing this little activity, I guess, together. Today is my lecture. The one tomorrow will be Daniel's lecture. If you haven't had him before, he's a lecturer who has taught engine mechanics, solid mechanics, structural analysis, and timber structures and stuff like that as well. And then next week, either towards the end of this week or I believe start of next week, you guys can start collecting materials and start building. I believe the balsa wood and all the other materials that you guys will be given is on the way. So it's being shipped over. And then in week 9, you can conduct some preliminary testing. So we'll tell you guys where the shake table is. It's essentially in the building next door to the civil building. And you can basically place your structure on, clamp it down, and do some initial tests. We'll keep it at a very low speed and stress. It's just you might want to figure out your building's natural frequency. I'll explain what that means in a second. And then in week 10, you can spend that time just refining your design before we do the final testing day. So the final testing day, we'll do a couple different tests, and then there'll be industry representatives there, there'll be academics there. It'll be a good fun day with lots of people. Okay, any questions about the project timeline? Okay. All right, so here's I guess the flavor and all that. What the project's about thematically, right? So you've got CEVSOC, the developers for this building, and they want you to design a student accommodation building in an earthquake-prone area, right? The more floors that you install, the more rooms they can sell. So essentially this will convert to being more points for you guys and your team, okay? So, first things first, I'm going to tell you guys kind of the limits of where and how. Oh, by the way, sorry, I saw a few people came in after I started, and I'll just give you guys a QR code again. And this is in case I go too quick when I'm talking. Having the slides up might be helpful in case you wanted to see or look at the numbers for a little bit longer on all the geometry of the building and all that, okay? Okay, so if you're not familiar, plan view just means top-down view, so bird's eye view. Elevation view just means side-on, so you're looking at the shake table or the building side-on. So in the plan view, right, the idea is that you've got some allowable construction zone to build in, right? So top-down, this will be approximately 300 by 300. I just realized there's a typo. It's about 300 by 300, which you're allowed to build in. You'll be given these balsa sheets. So I'm just going to put this microphone down. I'll show you guys this. You'll be given these kind of balsa sheets, right? Slightly thicker than this. And the idea is we'll cut it up in a way that you will kind of glue it together in the arrangement that you see in the bottom left there. So I'll just zoom in there a little bit. So the idea is we'll have 3 of these kind of, these will be chopped in half, and then 3 of them lined up will be glued together using these kind of cross-laminated strips as well, going that way. And that will be the base of your building. So that will be what you're building the rest of everything on. And the idea is that you've got the shake table platform. I'll show you a picture of it later. Sorry, I just realized I got to clip this microphone back on. One sec. Okay. It'll be clamped to the table, right? Okay, so looking at it from side on, the idea is that we want your buildings to be in a certain height range. So there'll be a minimum height and a maximum height. And your team can determine how tall you want to go. The taller you go, the more floors that you can build, and I'll explain that in a second, and therefore you can get more points, okay? But the taller it is, the higher risk that, like the more forces it will experience essentially. So there's a higher risk of it falling down. So the tallest you can go is 700 mil. The shortest you can go is 400 mil. So you want a building in that range, okay? The idea is that the base plate will be clamped down so that it's like attached to the shake table. And the shake table will shake left and right from the plan view, or actually both views. So we'll go in that way, all right? Any questions about the platform, the shake table? Nope, okay. Okay, next I have to tell you about the floors, the idea of minimum headroom. So we've got like as I mentioned on the last slide, we've got a height limit in terms of the maximum, so 700 mil, and we've got a minimum in terms of how low we can go, 400 mil. The idea is that the more floors that you construct, more suspended floors, you'll get more points. And I'll show you guys the points breakdown in a second. You get more points, but each of these floors has to have a minimum headroom, okay? So your little dudes in your miniature building have to be able to live there, you know what I'm saying, in the student accommodation. So you can't have it be too short, okay? And the minimum headroom is 150 millimeters, okay? So between each floor, there has to be at least 150 millimeters of height, okay? So that's 15 centimeters, all right, half a ruler. And then each of the floors has to be able to support a juice box, basically. We're gonna go to Woolies and buy these like apple juice boxes, and they'll have 250 mil containers. And the idea is that's 250 grams. So if you want to do any calculations, these masses, which are gonna sit on each of the floors, each of the suspended floors is gonna be 250 grams, all right? And then you have to have a minimum of one suspended floor, which just means you have to have at least one floor, right? And your building has to be at least 400 mil. Okay. Any questions? So these juice boxes are supposed to represent the weight on each floor due to the students living there. Okay. So hopefully the material stuff will make a bit more sense with the exact quantities that you'll be getting. So I guess I've kind of broken it up into 3 buckets, right? The first bucket is your sheet materials. Sheet materials looking like this, essentially. So it's kind of like a flat piece, like you can see. Prismatic materials, you can see at the front there. Those are kind of like the timber rods, right? So they have like a square section. And other connection materials, essentially, right? So I'll go through them one by one. So for the sheet materials, you're going to be given... it's going to be chopped up like this, basically, right? So it'll be half the length of what you can see here, right? And then you'll get some other pieces which are half that length. And the idea is that you're going to construct this base piece, which everyone will have, okay? So you'll just glue that piece on and glue that piece on, and you'll put some glue between the joints as well. And that's how it's going to attach to the shake table, okay? And that base is going to be 6 millimeters thick, all right? 6 millimeters thick. And it's made of balsa wood. So all of the wood that you'll be given for this activity is going to be balsa. And then in terms of the prismatic materials, you'll be given 2 sizes for like the rods, right? You'll be given the thicker one, which is 12.5 millimeters thick. And you'll be given a kind of thinner one, which is 6.5. So when I say 12.5 and it's a square, it's side length. All right, so side length is 12.5, side length is 12.5. And same with this, 6.5 by 6.5. You'll be given 8 and 6 of these respectively. And each of these will be 915 mil long, okay? So they look like this, all right, what you can see on the right. The other materials you'll be given are for your connections. So the members themselves will be made out of balsa, but the way that you put them together, you'll probably need these connections unless you decide to dowel them into each other. So we're given 4 rubber bands, but the rest is essentially available at the makerspace. There may or may not be some nails given to everyone as well, but essentially you can use infinite. Just go to the makerspace and ask for it. So yeah, you'll be given nails and you'll be given glue. So the glues which are allowed, which is all you can find in the makerspace anyway, is PVA, wood glue, which is essentially just PVA, and hot glue. So the hot glue gun as well at the makerspace. Any questions about the materials given? No? Okay. All right, so here's how you do well. Here's the point breakdown. Basically, this is kind of like scoring systems like D, C, B, A, I guess. So in the first row, right, this is how your structure performs on the testing day, okay? So there's going to be 2 tests that it's going to have to, like, survive, I guess, all right? And if it fails both of the tests, no matter how good your thing looks on paper or physically looks in terms of its aesthetics, it's going to be given a 0.5 score multiplier, okay? So you're going to get your points chopped in half. If it only passes one of the tests, but not the other one, you just have a ×1 point multiplier. But if you're able to pass both the tests, so it's a normal difficulty one and then a hard difficulty one, all right? If you're able to pass both the tests, you get a 1.5 times score multiplier, okay? And then in terms of how you actually get the points, right, it is these 4 rows. So the number of suspended floors that you have will give you 5 points each, okay? So if I just go back to this schematic, for example, this has 3 suspended floors. Suspended just means it's not touching the base, okay? So this would give you 15 points, for example. The self-weight per suspended floor, so we'll chuck your whole tower on a scale, right, and we'll divide it by the amount of suspended floors you'll have. And basically, this is just saying, like, if your thing's too heavy, we're not going to give you as many points as if it's on the lighter side. So if you're able to have like this strong like strength to weight ratio, basically, right? Okay, that's all quantitative, right? The idea is that there's going to be judges who are like from these big companies and also academics with the school, and they're going to do a bit more like qualitative judging, okay? So the 2 criteria they're going to look at, the first one is innovation and your explanation, because you guys will give like a brief explanation or speech about your building, correct? And that's you guys basically describing what you've done differently to other groups, right? So that's your innovation. Basically, you get more points if you are more innovative and if you kind of explain yourself better. And the other criteria is craftsmanship and aesthetic. So the idea is how well your building looks. And when I say craftsmanship, it just means like how nicely is it put together? Because if it's kind of just like cobbled together with duct tape and whatever, it's not going to look any good. Okay, that's the point criteria. Any questions about that? Nope. Fantastic. I'll just show you guys the loading stuff and then we'll take a break to do a bit of group discussion. So the shake table loading, essentially, we have 2 days, right? So the first one's going to be the one in week 9, which is the preliminary testing day. And the idea is that this is going to be a low amplitude cycle. So we're not going to try to break your building or anything. You're allowed to play around with the frequency to essentially find its natural frequency, which I'll show you guys in a second. And that will probably help with your design, and it can help with whether you want to add more floors or take floors away, things like that. And then the final testing day, which will be in week 11, you've got 2 tests, right? So when I was talking about the point breakdown before, I was talking about whether you pass 1 or 2 tests or 0. It's these 2 tests which are on the final testing day, right? So this is in week 11. The first type of test is going to be a constant amplitude and frequency. So when we input the amplitude, that's just how much it moves, right, on the shake table, and frequency is how fast it moves. And for the second test, we're trying to excite the building's natural frequency. So this will be dependent on your building, okay? So we're going to have a relatively low amplitude. It's going to be 2.5 mil. except we're going to slowly increase the frequency until your building starts shaking a lot, basically. And I'll show you a video of what that looks like now. So this was next door in the lab, and this was me and Jack the other day testing it. So this is for the steel frame that was already there. Makes a funny noise. But you can see that for this steel frame that was there, we excited the building's natural frequency by increasing the frequency up until basically starts shaking a shit ton. Okay, so that's the second type of test that you guys will encounter. We've run some kind of basic tests on like what frequency this might be. So for this full height frame, it was 950 mil tall, so that's taller than your building limit. The frequency was 2.2 hertz, right? So that's the amount of cycles per second. And we also tested the half height structure, aka we just like took the screws out from there and there, and so we're testing half that height, right? So about 525 mil, which had a higher natural frequency, as you can imagine. So it had a frequency around 4.4. So we had to shake it faster, basically, if it was a shorter structure. So that's something you might want to consider in your design. If you go for a lower structure height, it's better for the amount of like equivalent horizontal force that it's taking, but we're going to shake it faster in the second test. Does that make sense? So if you've got a taller building, it's going to have a more modest frequency that we're shaking it at, but if it's a shorter building, we're going to shake it a shitload, okay? Now, it doesn't translate like one-to-one because the way that you find natural frequencies through this formula, I wouldn't pay too much mind to this formula. What's best to do, instead of trying to run calculations on these like relatively complicated systems, is to come in week 9, test it out, find your building's natural frequency just through testing, okay? Because that's like first-hand evidence that you know what the frequency is for your building. Yeah, so the idea is that it's a function of the stiffness and the mass, right? So balsa wood is less stiff than the steel that you saw in the video, but it's also lighter. So it'll be something. I don't know exactly what frequency we're going to shake your building at, but it should be roughly in that range, hopefully. Yeah. Any questions? So what you saw there is like hitting the natural frequency. Another word for saying that is hitting in resonance, right, for your building. Okay. You guys can talk amongst yourselves, and I'll come around and just check everyone's up to speed and say hi and stuff like that. And you can also take a break. So if you need to go to the bathroom or get water or whatever, men's bathrooms on this level, girls' bathrooms upstairs, and the water's upstairs. So in level 6. All right, I'll come around. Hi, Ray. Where's your group? Damn. Who is it?
It's majority of the market.
Oh, yeah.
Reader will be Chris.
Oh, true. Do you have any ideas for life?
The only thing I got from the slides is like the point system. So it's higher, like what's the maximum? The taller it is, the more risk you take. So more points will be awarded.
Yes.
Quality of like it's a good design. If it's aesthetic or if it's like good craftsmanship.
And they'll be judged by engineers. The other thing is, if you have a shorter building, we're going to shake it faster.
Oh,
There's an inverse.
okay.
So there's a higher chance you do well in the first test, but higher chance you do worse in the second test.
But it's a good in general, like if you're aiming to build it higher, like that's how you school and register. Okay. I have a question.
Okay, yeah, no problem. You probably have more questions. It's very different. This one is similar, but the other one is a bit different. Did you go into this?
Yeah, it's really bad.
Oh, yes, that's true. There's going to be a reference.
Oh my god, we should sit down. Yeah, we are.
What's it gone? I gave them a message, but they don't show me. It's mostly the marketing. Yeah. Yeah, because he was in the room. We were like, okay, it's only got one more person. That's fine. They said because they're busy, so they're gonna watch it.
Would you be interested in maybe going back to I'm not gonna say this is anything.
Because I'm not like I'm not interested from this. I'm like listening and just doing like it's got.
How much is
Hey everyone, just a gentle reminder, we do have food at the back there. So if you do want to grab some food, maybe some snacks or drinks, all at the back, serviettes and plates provided as well. So feel free to re-energize yourselves while we wait.
That's literally what I thought. But then you got bonded together, responding by heart. Sure, is that the main thing that's mostly like flexible?
No, because I wasn't doing
Yeah. And then there'll be two pieces out on top left here, right? And this will just but yeah, here's the clamps and the clamps are gonna grip on too tight. If you have a bigger piece, something down the balls. Because balls are
Not a single word.
what is this?
Yeah, I feel it.
Yeah, she said
I set up the five in the place, so that's really efficient to time.
Go do that.
Like I think I have to touch on the way enough for
So these 6 no ones for the best, 3 no but how you reach this is to be able to hold it down.
It doesn't flow.
That's we have no idea what that's
How big flow it is? How big flow?
it's up to 4. Because you need to lose even if it's
I think it's just gonna be
Yeah, well, I'm gonna
it is pretty free like no stuff. It's only chat. No.
Oh,
Do you have a computer?
but later you might have bit more.
Do you have a computer?
Especially to look at
Where? Did you not answer the question that you
Oh, maybe, yeah, I guess.
It's quite translation.
Did you get the did you get the script?
It's like secondary library and it stands out as
So I asked one, go ahead.
based on very good execution.
I didn't realize how bad it's like a somebody actually there has
Was that the unseen question?
You present it with I didn't know we didn't make a slide here, so I was
Wait,
oh,
the first question, which is this is the last question. The one where they give you a list of.
Literally, like the only thing I've learned is like a bunch of math, concrete,
There'll be a bit more so you can divide the yeah, it's like one of those slides. Let me know. Hello. Liam. How are you? Yes, I'm good. You betting on the World Cup? Oh yeah, your friends don't. No, I'm just asking because you brought it up the other time. Oh.
So it's fun.
I say if you do it 25.
Okay.
Well, the max is 600.
Oh yeah.
Yeah.
No, but that's you want. But yes, you guys have to count the score.
yeah, I don't think that AI is saying anything useful.
Easy as you win. You're gonna win.
And then the chat to be saying,
How's the rest of
probably
That's a favorite.
yeah, there must be some logic behind
So it's up to you. You can put one and maximum be 4 just because of the restraints with the max building height and the clearance each floor is not the same height. And you do the technology. you guys
I don't like hey. I tried every single one of them.
Sorry, you guys are carrying.
I was 50-50 on class one and second one.
Hi guys. You guys
I felt like we should have
Yeah.
Yeah, are you all first years? Oh yeah, I know you did my 1300 workshop. Yeah. Yeah, you guys can wait for I like how it's in the second half of this, I'll go through the theory, and you tell me if your brain hurts. Okay? Because I'll do the type A style like
when you shake it and it
you
shakes.
need the theory really well, so you need to tune it to the right frequency. And also you need something heavy enough.
We use the video.
You can't just notice the
So
it's gonna be hard to
I
shape.
think the one thing is like the most
As long as the nails don't like spill over and that's all. Funny. Yeah. Any other ideas? That's what people are this. You might have more ideas in a second. I'll go do that now.
yeah, seismic stuff.
Okay. So recording? Yep. Okay. We will continue. So, okay. First we're going to go through cyclic loading. So that includes like context on earthquake loading. I'll talk about energy dissipation and then mention these other ones a bit, but those will be reserved mostly for tomorrow. But yeah, hopefully this should spark some ideas for you guys and your groups. Okay. So cyclic loading, right? I've kind of divided this. These aren't like official categories or anything, but I've just shown you a couple cases, right? So there's 2 on this slide, and there's gonna be 2 on the other on the next slide. The idea of a cyclic load is that it keeps happening over and over again, right? So if you have more cycles, that means it goes on for longer, right? And there's a couple of different ways that this, I guess, manifests, right? Here on the left, you can see linear force loading. So this might be, for example, in a lab, you might do a crushing test on, like, say, a concrete cylinder. If you apply some load and then it's kind of like a hydraulic press thing, right? You apply some kind of compressive load and then unload it and then reload it and unload it. That hydraulic press is going to potentially have a linear kind of shape in terms of the rate at which it starts loading and unloading. And then, so that's one type of case. Another case is like a sinusoidal load. So here you can see it in the context of stresses, right? So this is the case for when we do stuff in structural design related to fatigue, so fatigue loading. This is a little bit different to what we're going to kind of design for, which is more like seismic loading, right? The main difference is that for fatigue loading, you have a high number of cycles, in like the millions or billions, but it's relatively low stress per cycle. So an example is if you've got like a wind turbine or like in a wind farm, the foundation, right? So the footing, the bit of concrete underneath the windmill will experience this kind of fatigue loading. So constant loading and unloading, and it's going to follow this sinusoidal shape. So I just wanted to get you familiar with some of the terms, right? So as I mentioned, this is just one way that you can graph. You might see like a sine wave, basically, right? It's in the form of stress in this case, right? So the stress goes higher and then lower and higher. The amplitude of this sine wave is from the middle, so the mean stress value, up until the max or the minimum. So that's how much it kind of deviates from the center. Each cycle, right, is kind of like a cycle is talking about it from like a time point of view, right? So how long does one cycle take is like the period, right? And then the stress range is just the difference between like the peak and the minimum. Speaking of which, yeah, so that's the minimum stress, that's what the max stress would be. And you might see this term as well, stress ratio. So that's the ratio of how little the stress can be divided by how big the stress can be, right? Okay, so those are some basic cases. And now we're going to relate this more to our project. So these two cases will kind of translate to our project a bit more. So case C is basically like during earthquake events, they record using like an accelerometer how much shaking the ground does, right? And they record this in the form of acceleration, right? So here on the y-axis, right, you can see acceleration data for an earthquake, and then how it varies over time. So it's very sporadic. It doesn't follow this nice, I guess, like constant amplitude or anything. And yeah, there's plenty of reasons for this. It's got more than 1 degree of freedom. That's like the main thing. But the idea is that for earthquakes, what you have to realize is there's a relatively low amount of cycles. When I'm talking about low cycles, I'm not talking about like 3 cycles. I'm still talking about like, could be like tens or hundreds or thousands or whatever. That's still considered a low amount of cycles. It's just there's a high amount of stress in each of those cycles, right? So that's what causes buildings to fall down abruptly, etc. Okay, so we're not going to basically do complicated maths with acceleration. We're going to try to simplify this as much as possible so that you guys will be doing as much of the designing and building parts as possible, not as much using maths and like doing analysis, right? I'll explain that a bit more in a sec. But yeah, anyway, so our project, what I'm showing you guys is the inputs that I took a picture of this the other day when we visited the lab. These are our inputs, right? So what we can control is the amplitude, right? So the amount of the amount that the table like physically moves, and the frequency, so how fast it shakes around, right? In other words, yeah, how many cycles per second is what Hertz is, right? So we can control this. The dial says it only goes up to 3, but if you type in this box, it can go higher. So that's how we got to like 4 and stuff. Same thing with the amplitude, we can go higher than 2. But not by much. Okay, any questions about this project and the sine wave, cyclic loading, that kind of stuff? Okay, so let me introduce you to the idea of earthquake loading and how we design for it in structures just generally, right? So the thing is about earthquakes is that they're different to how we do the maths for other types of loading when we apply it to structures. So for one, it's not static, right? So in Eng 1300, which I think all of you guys have done or are doing, the idea is that loads and how we apply them, I guess a lot of the time in structural engineering, is we look at equilibrium. This is the idea that you've got a building and you place some kind of weight on it, and it's a static load because that weight doesn't move or moves very, very slowly, okay? So the difference with earthquakes and these kind of static loads that you normally see is that they're dynamic, right? That's the first thing. So similar to wind, okay? So wind is applied horizontally, and it's essentially this dynamic force that we translate into an equivalent static force. Okay, anyway, that's enough about wind. Even more complicated than that is earthquake loading, right? Because not only is it a dynamic load, it's not even a load to begin with. It's not like literally, like, we're not literally applying like a horizontal force at this level, horizontal force at this level, etc. What's actually happening is that the force is shaking the seismic weight of the building around, right? Sorry, not the force. The displacement of the earth itself is shaking the building around, causing its seismic weight or its self-weight to accelerate through this displacement. Well, in the case of our shake table, yeah, the shaking of that table, right? So it's causing these like individual levels to accelerate, okay? That's the first thing. We're gonna pretend that it's horizontal, just for simplicity, like purely horizontal. Okay, so I'm gonna show you the earthquake standards. And I know some of you guys are like first years, second years, whatever. And you might not have industry experience, etc. How this project is going to really be different to what you're used to probably in your courses is that if I show you a formula, if I put a formula in front of you, that's not like you can copy it down if you want, but like that's not like the solution. You know what I'm saying? I'm going to show you guys a bunch of formulas, and I want you to keep the theory in mind, but you could honestly do really, really well in this project without doing a single calculation, okay? The idea is that it's not a maths problem to solve. It's a design problem. So I'll show you what that means in a second, okay? So don't go down this rabbit hole of trying to figure out the answer through calculations alone, because the group that wins might not even do any maths at all, okay? You know what I'm saying? All right, so that's a fair warning, all right? But I still want to kind of explain where the formulas come from. So I want you to focus on the physics of this, not the maths, all right? That's the important distinction. So how the code, so for context, right? If you're not in third year yet, you might not have done not structural analysis, steel structures or concrete structures, or these kind of more applied third year courses. What they teach you in these courses is basically, here are the Australian standards. You have to design for this. You have to follow these formulas, etc. So that's what's in like these kind of books, right? So they teach it to you from a very like applied point of view and not really from first principles, okay? Which is fine, but they're all based off first principles essentially. So that's what you're seeing here. You're going to see a bunch of notation that you might not have seen, especially if you're in like first year, for example. But this is how it's written in the code, and specifically, it's going to be tailored to Australia. All right, a lot of these codes, either Australia only or Australia and New Zealand. So here's what is called the capacity equation, right? So on the left, right? So these two parts. The idea is that your building is X number strong, okay? So that's your design capacity. That has to be stronger than the design action. The design action is the forces that you put on your structure, which cause it to break, okay? So that's essentially the two parts of this equation. Basically what the earthquake code outlines is how to calculate the design action, okay? And there's kind of like subcomponents to this, right? So there's the vertical component and the horizontal component. And essentially, in the vertical component, there's another two components, okay? But we call this the seismic mass. There's your dead load from the building self-weight and live load from the foot traffic, okay? Don't worry too much about this 0.3 factor, okay? You can completely ignore it, essentially, if you want to do calculations. The reason is it comes from probability, okay? So the difference between G and Q is G represents your dead load, so the loads that are always going to be there that you can't get rid of. For example, the self-weight of the building, right? So in our case, it's timber. Okay, so it's how heavy the timber is. It's always going to be there for the duration of what we're doing with timber. And then Q would be the live load. So I'll give you an example of live load. If you're in the elevator, right, the self-weight is the metal, right, of the elevator itself, the elevator shaft. Not shaft, the elevator. The live load is people being inside, okay? So we know that people go in the elevator and then they leave and then they go in and they leave and all that. So the idea with live loads is they come and go, okay? And you don't know for sure how heavy it's going to be inside there, all right? So they're variable. And so that's what I mean with probability. Okay, you don't exactly know how much load is going to be imposed, essentially, right? For our case, we know exactly how much load is going to be there, okay? We know it's going to be how heavy your juice box is and how heavy your structure is. So take everything as unfactored loads, okay? Unfactored forces. The idea is there's no probability component to it, okay? We know exactly how heavy everything's going to be. Okay, so that's seismic mass. The other part is horizontal load. So it's kind of confusing to look at this because it's basically these are vectors, right? So the idea is that you've got a vector arrow that's kind of pointing downwards, and horizontal loads are the ones that are kind of going sideways, okay? So can't really directly add them because they're directional. I'll tell you how we calculate this horizontal load, okay? And it's called the seismic force. So yeah, the Australian code is really complicated. It has all these kind of components to it, right? like for example, how much seismic force is going through your building is going to be a function of how tall that building is, and the risk of the earthquake in that area that you're building in, and the soil conditions, right? So how squishy the soil is. Obviously, we're dealing with a model, right? So it's a scaled down version of a real building. So it's not going to have a lot of these be able to translate one for one, but we're going to basically look at what they do in the standards and interpolate it a little bit into our design. The way that the earthquake code is structured is into 3 design classes, right? So it's called earthquake design classes. There's EDC1, which is a simple analysis that they do for shorter buildings in less earthquake prone areas. And there's going to be EDC2, right, which is more complicated for taller buildings. And EDC3 requires complex analysis, and this is for like skyscrapers and stuff, right? The way that they handle it in EDC1, this is a simple analysis for low-rise buildings, is basically saying that you can calculate the seismic load, which was the vertical load from before, right? And your building has to be able to take 10% of whatever that load was, but going horizontally, and see if the members break, okay? Yeah. Any questions about that? So this is like the simplest kind of analysis you can do. But what I wanted to kind of tell you guys about is the second way, because this is, there's a lot more to it, basically. So this is basically saying we've got this really complicated system that is ground acceleration, causing your building to move around and stuff like that. We're going to do an equivalent static load. An equivalent static load is just saying we're going to pretend that, sorry, I'm going to skip forward a slide. We're going to pretend that the force distribution is purely horizontal and it looks something like this, okay? And then here's how we would go about and get those numbers. So the first step is you figure out the vertical load, right? The seismic weight, right? And you have to also figure out the total seismic weight. So that's just all of the weight of the building, basically, right? Including the juice boxes. So that's WT. And we have to calculate something called the base shear. So if I show you the next slide real quick. The base shear is basically saying this big fat right arrow, which represents the total force at the base, is going to be equal to all these smaller arrows going to the left, okay? For the system to be in static equilibrium, okay? So the idea is that that number is a function of 2 things. First one's the seismic weight, which we can calculate just by adding all the vertical force, and multiplied by this thing, okay? Which looks pretty complicated, right? It's got a pretty cool name, actually. It's called the spectral shape factor, okay? And then this is a function of the period. So T is the period of the building. In our case, we're going to be dealing with the natural frequency for the second type of testing, okay? So all you really need to know about this factor, right, is it's an amplification factor. For example, if it's 2, it means that the natural frequency of the building makes the load 2 times bigger than it would normally be. Okay, and if it's like 3, it would be 3 times bigger than it would normally be. Okay? Okay, it follows this graph, and there's a few components of this graph which I'll try to break down. So, for a real building, it depends on what the building's founded on. Okay? So, A is strong rock, so this is the strongest type, and then E is squishy soil, basically, right? And the idea is that squishy soil is worse than strong rock because if your foundation is squishy, it's less stiff, okay? And it's going to amplify the amount of shaking, okay? Oh, sorry, I didn't really. Okay, so in this graph, right, all we need to basically interpret from this graph is the fact that where it peaks is your natural frequency, and this kind of y-axis is your amplification factor. So for the strong rock, it sits around 2.5 when it hits natural frequency, and for type E, it sits around 3.5 when it hits its natural frequency. So you can basically interpolate this and say, okay, if I wanted to do some kind of calculation on this during the resonance, which is the second type of testing that we're going to do, whatever kind of static load that you have is going to make it about 3 times worse, right, than we would expect. And then here I've like omitted a bunch of stuff from the real standards for the sake of simplicity. So just continuing on from that for EDC2, the idea is that you have to essentially distribute these forces based on the height. Okay, so this is kind of a concept you might want to keep in mind for your building and where you decide to put the floors. Basically, the idea is that where you put the floors, or the higher up it is and away from the ground, the higher equivalent static force that it's going to have. Right? So the top level is going to experience the highest percentage of that load. Right? So in this particular scenario, for example, let's just say, for the sake of argument, the top floor, or the center of that juice box, that level, going horizontally, that might take 50% of whatever the base shear was, okay? And then, for the sake of argument, the middle floor would take something like 30% of whatever the base shear was. And then the lower suspended floor is going to take, say, like 20%, something along those lines, okay? And it really depends on, it's a function of the height of each of these floors and how far it is away from the ground. Okay, so, or from the surface of the ground to the middle of the juice box, okay? Okay, so, yeah, K factor is basically saying whether this is linearly distributed, so if I draw on this, right, whether this shape is like a triangle, or if it was instead more like a parabola, or whatever you kind of call it. If it's like a parabola, that would be K is equal to 2. If it's like a straight line, it's K is equal to 1. And the idea is that there's a linear interpolation that you do based on the period. From my testing, I found that everything's linear. So you can assume kind of like a linear triangular distribution. Okay? Any questions? Okay, so you just assume it's triangularly distributed, these forces, right? It follows that shape. Okay. So EDC3, this is essentially if you've got a building that's high risk of being in an earthquake zone in real life, or it's very tall, or some combination of those two things, you have to model it in a program called ETABS, or equivalent, and it maps on your acceleration, like your real acceleration data from an earthquake that's actually happened before. And it's got all these kind of parts moving at once. For example, the way that they would really do it is like, just pretend this top floor and this weight on it is going to the left, whereas this one's going to the right. And then you've got all these kind of overlapping oscillations going on. That's kind of what the program does, and it does a lot of complex simulation on that. But obviously, we're not going to deal with that. I'm just telling you guys that for context. Okay. Any questions about that or anything? All right, so that's kind of how cyclic loading works. I'm going to tell you about the idea of energy dissipation. So this is the main thing I would say that you have to consider, and kind of what makes it different to DESN 1000, what makes it a lot harder. So in DESN 1000, in case you haven't heard of it before or you didn't do this project, there's a balsa wood tower, and you've got this car that goes down a ramp and smashes into the side of it, okay? And yeah, there's like all kinds of complicated things about that in terms of there's going to be a dynamic force of some sort. But what makes our project different to that one is that one, you just make a really fucking strong building. Okay? You make really stiff connections and it won't break. Okay? Obviously, how you distribute the strength of each of those members in that building will matter a lot. But for our project, the members, the actual like columns, the beams, everything, they don't actually need to be very strong. Okay, that's one, because we're not directly putting any loading on it. Like we're not hitting it with like a car or going down a ramp, etc. Right? That's one. The second thing is we actually want to consider how we design the connections quite considerably. If you slap a bunch of glue in one spot, it's going to make it stiffer, which you might think is good, but there's not going to be a method of energy dissipation. So it's going to highly stress these glue joints. So a lot of this project is going to come down to how you detail these connections, okay? And whether you perform well in doing that. So I'm going to tell you about the idea of energy dissipation. I'm going to have to give you a bit of like physics theory though, so I know it's like too much for a non-uni course. Okay. The idea is that from energy conservation, right? So this is like work energy methods, basically. there's conservative forces and non-conservative forces. So a conservative force is basically potential energy. So mgh, the potential gravitational energy, and spring force. So yeah, for the sake of buildings, it's going to be your internal spring force. What we want to focus on is looking at these type of energy. The energy that comes from non-conservative forces, right? So this is basically, for example, friction, or kind of these resisting forces, which is going to dissipate energy out of the system, okay? So here's a formula for energy, right? And again, this isn't about doing the maths behind it. It's about thinking about where this maths comes from and thinking about the physics behind it. Your energy dissipation is going to be equal to essentially what frictional force that you have multiplied by the distance that is in the direction of that force, okay? So when I'm talking about the kinetic friction force, it's like, for example, you've got two surfaces sliding against each other, right? At that interface, you're going to have a friction force, and if it's moving, it'll be kinetic. And then basically the energy dissipated will be that multiplied by how far it's moved, so the distance, okay? So I'll give you an example of like something, I guess, physical from your pencil case, right? So if you've got two pencils and you've got this rubber band that's tying them together, okay? And it's like tying it pretty tight, so it's got a good amount of pressure between those two things. And if you think of me pulling those two pencils like away from each other, you'll see that the rubber bands they'll be tight, and they're going to apply a normal force, and there's going to be friction between the rubber bands and the pencils, right? This is a form of energy dissipation. So the idea is that the distance that you've moved is your work done distance, and it's going to dissipate a lot of the energy through friction, right? So that's one kind of method that you can think of for dissipating energy. And there's a few different ways you can do it. Friction, interlock, which is basically friction but on a bigger scale, and plasticity. So if you can somehow figure out a way for your nails, for example, to yield, that ductility that you get from it is going to dissipate energy as well, okay? Through strain energy. And you can think of how you're going to design these joints, right? So if you've got a perfectly rigid joint, for example, I draw it. So you've got really like thick kind of columns and beams and that kind of thing, and you've got a lot of glue and all that. It's not going to like it very much when it rotates, okay, basically. And it's going to stress these glue joints very highly when the shake table moves, right? So other ways you can think of connecting these members is through, like, for example, these hinges, all right? And it's going to lose friction. Sorry, it's going to dissipate energy through the friction between these two surfaces. For example, so from the white material to the red material, and from the red material to that white material. So there'd be two friction surfaces there for this kind of woodworking hinge. There's several layers of friction there, etc. So that's one way you can think of dissipating energy. So this one's translational, right? So moving two pencils between each other with a rubber band that's tying them together. And rotational is another one between the joints. Okay, so Daniel's going to talk about these last few ones a bit more than me, but I'll just give you an introduction to them. Lateral stability is basically you've got a building, you've got these vertical loads on it, right? And wait, I might just draw something quickly. Sorry. Okay, so you've got a building, right? So you've got a frame, you've got some like vertical forces that are applied to it. It might go from this force to, like, this force will be applied on a beam, for example. It'll be distributed into the columns, right? And it's going to work its way into the ground where it will be equilibrated. The idea is that if you've got horizontal forces, right, like wind, there's no clear path for this to go. So it's going to cause the building to displace heavily, like this, like move to the side and deform. So one simple way that you can deal with this is through bracing. So if you've got a brace that goes like this, this force is going to have a horizontal path into the ground. Whereas if you did the brace the other way, it's still possible. So the force travels through compression in this member, and then it's going to be pulled by this diagonal member in tension, and then work its way into the ground that way. So essentially bracing, which is what you see on the right here, bracing is one way that you can stabilize a building from horizontal forces, okay? And sometimes you see both of these cross bracings, right? So one helps in tension, one helps in compression. Usually they help more in tension than compression, but anyway. Another way is through shear walls. So shear walls is another very nice way to stabilize a building horizontally, and this is more common for dealing with earthquakes, right? So in a real building, right, we're gonna make it a bit more complicated. You've got all these levels. Yeah, let's say the levels look like this. And then basically you might have a big concrete, it's basically a vertical beam, right? So it's a big concrete beam. It's like a fixed support at the bottom. And when a load hits this cantilever beam, basically, so if you think of Eng 1300, you might be more used to seeing it like this, okay? So that's a cantilever beam with a point load at the end. All right, that's essentially what's happening, but we rotate our head 90 degrees and it looks like that, okay? You've basically got a big concrete beam that wants to do that, okay? So that's one way that you can transfer these horizontal forces into the ground, and that's what they do for a lot of, like, I guess, high-rise buildings and student accommodation. So if you think of like a modern-looking building, commercial or student accommodation or something, so like, you know, the escape building in Anzac Parade, for example, modern buildings really like to have glass on the outside, right? And glass is not load-bearing. So what they'll have is like an elevator shaft, right? Is basically 4 walls coming up, right, in a big box shape, right? Elevator shafts and stairwells also have these concrete walls. Those are basically shear walls, right? So in the kind of middle, sorry, I'm kind of talking maybe too quick. So if I looked at a student accommodation from top down, it might look like this, like the footprint, and this on the outside is all glass, for example. And for example, there might be an elevator shaft in the middle, and it's got this like 4 walls, concrete box, right? So shaking going this way is going to be you're calculating it as if it's like a rectangular beam, right, or hollow beam, right, made of concrete. And you're checking it as if it's a beam, like going that way. Anyway, yeah, so that's shear walls. The idea is that, yeah, they stabilize the building as if it's a big vertical beam. Material considerations. So this is going to be pretty important because you guys are dealing with timber. So balsa wood, right, it's a type of timber. It has a grain direction, so be very careful about how you orientate everything. If you think about it, give you an example, tension, right? So if I pull a bit of wood along its main axis, right? So that long axis there, it's actually pretty strong. Like timber's pretty strong in tension, but if I pull it such that, yeah, I'll show you on this, right? So I'm going to put this down for a second, the microphone. If I pull this board like going this way, so that way and that way, it's actually pretty strong, right? But if I try to pull the fibers apart, because these bits of wood, you can imagine them like straws, right? So each fiber of wood is like a straw that's bundled together with like natural wood glue. It's called, the cellulose and lignin. Lignin's the natural glue in between these straws, right? So if I try to pull these fibers or the straws apart in tension going this way instead, it's just going to fail at the glue joint, right? It's going to fail in the natural lignin interface between the straws rather than the straws themselves breaking. Does that make sense? Whereas this way, we're pulling on the straws, which are a lot stronger. The straws are the fibers called cellulose, right? So there's kind of two parts to to wood, right? There's the main material, which is like the straws, right? The cellulose, and the things binding them together is like the glue, right? Which is lignin. So just be really careful of these grain directions, right? Just think about how a bundle of straws would actually behave, right? That's basically how wood behaves. And Daniel will be talking about this more tomorrow. And ductility. So if you want to do something with the nails, right? They're made of metal, and they might have a ductile curve like this. This extra strain energy is going to basically result in a lot of energy dissipation. So if you imagine a paper clip, right, like a metal paper clip, and imagine I got the paper clip and I bent it back and forth over and over again. If you feel it afterwards, it's actually kind of hot, like there's going to be heat loss, and that's from the metal ions in the metallic lattice from like a material level rubbing against each other and losing energy through internal friction. So that's one way that energy can be dissipated through heat, right? And which is a type of friction, which is like very, very microscopic, right? The other thing you can think of is the fact that wood's ductile. So if you have like some kind of dowel joint, for example, say I wanted to connect two bits of wood together and I dowel it, right? So I cut it in such a way that the pieces like interlock into each other. There's actually a bit more ductility in that just because the wood itself is more ductile than, say, glue by itself. Glue has no ductility, but wood has a bit of ductility. So you can abuse that a little bit to see, yeah, to basically have better earthquake or seismic loading properties. Connection detailing, so this is like how you connect bits of wood together. So this is like a dowel, like I kind of drew on the last slide a little bit. You're not really going to be able to do a lot of these ones. I don't know why I included them. That's like metal plates and stuff. You might be able to do gussets. So if you want two bits of wood connected together, you can connect it with like another bit of wood on the outside, like a little rectangular or triangular piece that you stick on, either with glue or with nails. And so it might have a bit more rotational capacity. And these are just classic butt joints. The idea is if you just chuck glue between the bits of wood, then that's one way to connect them. Again, the glue will have very, very little ductility. So the main point of this project is not to make the stiffest possible joint that's super rigid, because your structure is not going to like that very much. All right, it's trying to think of the best type of joints so that energy dissipates the best way possible. Okay. All right, I'm going to leave this on the screen, but I'll just quickly explain a few of these, and then we can kind of do a bit of discussion, and then, yeah. So hysteresis, this is like a science experiment, like a high school physics experiment, but if you like load and unload a rubber band, you're going to see that there's kind of like two curves that it follows in terms of, yeah, like there'll be like a loading and unloading path, basically, and they don't actually follow the same path, right? So in the space in between, if you were to graph it in that loop, that area on that graph is actually the energy that's lost due to friction, or internal friction, and so that's called hysteresis. That's the idea of that is that the structure remembers at what point of stretching is at, and yeah, the energy lost in between is like something you can calculate, right? If you want, but yeah, just thinking of rubber bands in general, that's one purpose of using them. They're a method of heat dissipation or energy dissipation. Okay, Tectonus, right? So if you Google Tectonus, there's actually a brand, and it's a brand which specializes in kind of earthquake-resistant connections, right? And it actually behaves very similarly to the pencil analogy that I was talking about earlier. So you've got two pencils, and you've got a rubber band that's kind of like binding them together. And if you think of like an earthquake causing these pencils to slide against each other like that, that's basically what Tectonus does, except you've got, instead of rubber bands, you've got these metal springs that want to clamp together. And you've got these kind of teeth, right? So this is a mechanical interlock, these teeth. So when I'm going to zoom in a little bit. So let's say this is the starting point for it. If you pull either end apart, so the orange thing is in tension, these teeth are going to kind of bite, not bite, these teeth are going to like rub past and interlock, and there's going to be like energy dissipation, right, in the system in that way. Or if you push these two orange parts together, like so, like the orange thing's in compression, and it's going to do the same thing, just going the other way. So the teeth are going to slide past, and there's going to be a bunch of like friction, for example, like so. So you can kind of model how Tectonus does it through kind of like a rubber band analogy, if you like. Oops, that was my appendix slide. I've got two, but yeah, we won't deal with that yet. Okay, another one that's quite probably OP is rocking shear wall. So if you've got some kind of shear wall, like I was describing earlier, and let's just say you've got, so here it would be like a post-tensioned tendon, right? So think of like a skipping rope, right? Except instead of a skipping rope, it's made of metal cable and it's cast inside a concrete shear wall. That's basically like a rubber band, right? You've got a rubber band connecting from the bottom to the top of the shear wall, right? If you imagine, if this is your shear wall, right? If you imagine it rocking back and forth, but with a rubber band tying it, it actually is capable of doing a lot of energy dissipation, okay? Keep in mind the rocking shear wall. Base isolation, so this is probably one of the more, other than tune mass dampers, right? This is probably one of the most famous ways of dissipating energy. And that's like having roller joints basically at the base of your structure. So we don't actually give you like circular rods, but you can kind of get those like square rods and either like file them down or sand them down yourself, or just use you can use it as like the square ones if you want. And if you imagine those squares, let's say they look, actually I'll just drill them in circles. You got circular rods, like here, here, and here. At the base, and your table's shaking, the whole building doesn't actually experience as much horizontal force because there's a bit of lag between the energy transfer at the acceleration transfer at the shake table. It has to go through the spinning of the rollers before it reaches the building, right? So that's base isolation. They do this a lot in real life as well for high buildings. Some appendix items, I'll show them if they're needed, but this is just like really where the theory comes from. I'm sure this might make you gag or something, so I'll just leave it on this. I'll go back and forth if we need it. But yeah, anyway, I'll leave this here for you. I'll come around and then after we do some discussion, yeah, that'll be end of it today. Okay. I'll come around. Okay. How you guys feeling? Yeah, I can tell. I think he has so much confidence. That's not bad. But yeah, did any ideas come from that second half?
I guess more like the absorbing the energy stuff.
Yeah, they'll be like the main part of it. Yeah. As in like, it's gonna be hard to figure out. You got this though.
So
I believe in you guys.
it's like you're not doing it by calculation. The best way to find out is by guessing and checking.
Yeah, I wouldn't say guess and check's the best way. The best way is doing research of how these systems work. But it's better to understand the physics and apply it. So that's like engineering, right? Than running calculations. Running calculations is what like a mathematician does, right? Well, it's also how they test you in uni, right? Because you guys are universities, you're going to see this throughout your degree. There's going to be a very distinct difference between how you engineer something in real life and how they test it to you in uni. Because in uni, they know the answer already. They just want to check if you know the answer. Here, you're going to do whatever you want. So you can be as creative as you want and just try to problem solve it.
And then like how big of it
Yeah.
is?
Okay.
On top.
Let me know if any ideas come up. We can discuss it too. Confused? Or
So for what I've got, theory-wise, like you said, just kind of like throw out the calculations and then just apply the theory. Like,
yeah,
for
you can
example-
do very basic calculations. It helps, but don't get hung up on it.
Yeah, like it'll be too complicated, too many variables.
Correct.
And at the end of the day, like when we were designing it, like the structure is not gonna be fully like what we put in like a like for example space gas. It's not gonna look the same 100%. But like you said, so like things like glue, like don't use too excessive amount because it doesn't dissipate energy enough. Was there any other like building factors that we should consider?
Design the connections and engineer the connections in a way that dissipates energy. That's the best way to do well in this.
Yeah. So what would you say like how I want to be able to do it?
There's a couple of different ideas that I showed you. A bunch are on this slide right now.
Yeah.
I won't tell you what the best one I think is because I don't even know what the best one is.
Yeah.
We'll see. But this is where the innovation comes in, right? Like we're not giving you a problem that's like linear. It's not just going to be plug these numbers in and find the best number. It's going to be up to you and your creativity and your group's creativity to figure out what the best thing to do is, because that's
Well, you were mentioning a lot about rubber bands. Because I was just over here.
that's why we're limiting you guys to 4 rubber bands, because they're really OP.
Oh, okay.
Yeah. So you'll find the rubber bands are very, very OP.
Are they like, what? Am I using the rubber bands to connect joints? Is that like the alternative?
Yeah, yeah. Well, you can do whatever you want.
Oh, I could also like stack together wood, like bunch them up with it.
You can do whatever you want, right? As long as it's within the parameters that I showed you in the first half, you can do whatever you want.
Okay.
Yeah.
I'll think about it then.
Yeah. Discuss with your group as well, because this is not a simple problem.
Yeah.
Yeah, there can be like over 10 good answers. Probably more. So yeah,
I'm good.
Interesting though?
Yeah, interesting. Very interesting.
yeah. Hey guys, did that spark any ideas? Sorry? Yeah. It's not as simple as it looks at the start, hey. The best thing to do is study real buildings, see how they deal with lateral stability and energy dissipation. And take inspiration because they feed up very much. And that's where the innovation comes from. Let me know if you have any ideas there or any questions. Still confident or more confused? Yeah, sorry, I think so I'm kind of telling you guys this now, so you can just get better. Oh shit, there's a bunch of blue already. It's coming all these. So yeah, think about oh, you can do everything. It's just your music buckets. So we're only going to use 4 rubber bands. 4 rubber bands? Yeah. Rubber bands are OP. You'll find. You get infinite nails, but it's not like nails. Adding more nails, I think, is better.
Oh, I guess the match is silent. Oh, there's the box.
No problem.
What is the way to like?
No one's have a This is my iPad case.
Let's talk about whatever they can make space.
Even more.
But like the idea of like you have like your like
I think it's like it's execution, everything's tough. It's just you look at all the groups and see how similar they are. Very good.
so like there's a limitation. You have 3 on big sheet, 2 medium.
Okay. Last thing I'm going to do before I end the recording is just talk about the appendix items that I've got lined up. You don't really have to do calculations related to it, but I think it's still interesting to know. So if you decide to take structural dynamics, or for whatever reason, I think this is in like physics 2, which I don't think you guys really have to do. Okay, think of like a mass, right? And it's attached to a spring that's just dangling, okay? And if you think of kind of the graph that this follows, it will look maybe something like this, like a sine wave, and it's going to eventually dissipate. So the idea is that that is going to end up becoming flat after some time. So the physical system is literally just a spring, right? But how we would model this mathematically is something probably more similar to this. So you've got the mass, but the spring actually has 2 parts to it, right? The spring has the literal spring, oh sorry, the mathematical spring. So if it was just a spring, this motion will continue forever. Okay, so if you've got a spring and if you just applied all your understanding of mechanics to the spring, it just oscillates infinitely and it has a constant amplitude. Okay, what stops it from doing that, and we know this in real life, is this component here, which we call a damping coefficient. Okay, now what this literally is, like what it's drawn as, is like a very old school engineering kind of representation of what it is. It's called a dashpot. So dashpots are from steam engines, right? And it's just carried through until like modern terminology. But they like the physical representation of what it is now is like something that's used for cars, basically. So what you can see here is a shock absorber. Okay, so inside here is like some kind of oil, right? And kind of behaves like, you know, a balloon pump. Kind of behaves like that. And the idea is that it slows down, no, not slows down. Okay, I'm just gonna say the word slow down, it's not the best word. Slows down this oscillation, okay? So it dampens it, okay? So that's damping coefficient, all right? And so if you do the force analysis, you get F is equal to ma, you get all these things. So these are the force components. So in the case of this, it would be, the driving force would be gravity, mg, and you've got these two components, right? You've got the spring component and the damping component, and you can do the net force is equal to the mass times acceleration. And yeah, you got the spring constant, damping coefficient, etc. How this kind of applies in our case is, instead of a spring and then a mass dangling off of it, it kind of is this inverted pendulum for our building. So we pretend that our building's like this kind of cantilever spring thing that goes up, and it wobbles side to side. Yeah, that's kind of how we would do it. Hysteresis, I think I kind of explained that before, but that's just another thing I wanted to include. And yeah, so damping ratio, this is another thing you might want to keep in mind. So basically everything has a different damping coefficient and it doesn't really mean anything by itself. What really matters is the damping ratio. So the idea is that there's an ideal number for every system called your critical damping coefficient, and your damping ratio is what percentage your system currently has divided by that ideal ratio, divided by that ideal number. So I'll give you an example. If you're pushing your friend on a swing, you know those swings, there's a side on, and there's your mate, and he's sat down like so, and you're pushing over here, right? Your mate swings that way, and then when he swings back, if you push him with a perfect amount of force, right, the swing stops completely, okay? And if it stops completely with no additional motion, that is a damping coefficient of 1, critically damped, right? So no motion after that, right? So that's a damping force that you're applying, right? If you push lightly, right, it might become underdamped. So the idea is that this swing will continue, but it will be lower, right? And then if you overdamp, it'll just kind of bounce back. And yeah, anyway, like overdamping is not really in the realm of structures, right? What happens a lot of the time is underdamping. So for most buildings, damping sits around 5% or 10%, right? Which basically means that the energy will dissipate. So say you stop applying forces, the energy will dissipate after about most of the energy will dissipate after about 4 or 5 oscillations of the building. All right, so it's going to slowly taper off. If you've got a tuned mass damper, this is aiming for closer to 30%. So the tuned mass damper will reduce the amount of cycles that it keeps going for. Okay. Anyway, yeah, that's pretty much all I had to say. So I'm going to stop recording.